let's go ahead and get started. It is now 10 after, so welcome back to MAT1841. So last time, we spent a lot of time on constructing random hash functions. So we got to see some nice applications of Galois fields. Today, we're going to move on to using some of these hash functions, and we're going to use them to construct sketching algorithms for estimating frequency moments. In particular, we're going to spend some time and actually delve into the count distinct sketch, which I mentioned a little bit last time with my hyperlog log stuff, but we're actually going to go through the math and prove that, well, simpler variants of it work, though we won't actually go all the way up to the modern version. So let's get started, and let's talk about our model. So consider a sequence A1 through AN, which are all in M. So the set of integers from 1 to M or 0 to M minus 1. I'll be using the two interchangeably, so hopefully that's not too confusing. With N and M both large. And so this is what we're going to call a stream. And we're going to get too many items to store everything. And this is going to make us sad because we want to know some things about the overall statistics of the stream. So what can we do? And what do we care about? So for any S in M, we're going to let F sub S be the number of elements in the stream that are S. Okay, so this is going to be called the frequency of S in the stream. And we're interested in a couple of different things that we can define this way. So we're going to be interested in things called the frequency moments. So for any P, that's an integer, a positive integer, the Pth frequency moment of the stream is F sub P is equal to the sum over S from 1 to M of S F sub S to the P. And so for the first couple frequency moments, those are all useful things that we care about. And they have nice, in many cases, they have nice intuitions. So what is F sub 0? Well, we're going to use the convention here. I know this is not always standard, but we're going to say that 0 to the 0 is equal to 0. Non-standard in some ways. But then F sub 0 is going to be equal to the set of unique items in A1 through AN. And that's going to be the number of distinct symbols. So this is precisely the count distinct problem that things like hyperlog log solve, which we're going to work on a little bit later. And yes, I know 0 to 0 equaling 0 is a somewhat non-standard, but it works for our use case here. So what are some of the other frequency moments? So does anyone want to tell me what F sub 1 is? Yes, it's just N, just the length of the stream. Yeah, because the frequency, it's the frequency moment. Yes, yeah, no, exactly. Not the items themselves. Yep. But yeah, so that one's also pretty easy. That one's the arguably the easiest to compute of all of these. You just count them, or you can use various other ways of counting them if you want to be clever. And an F2 happens to be useful in computing variance. And by variance here, I mean variance in occurrences of elements. So note that 1 over M times the sum from S equal 1 to M of F sub S minus N over M. If we square that, that's just going to be 1 over M times the sum from S equal 1 to M of F sub S squared minus 2 times N over M F sub S plus N over M squared, which is equal to 1 over M times the sum from S1 to M of F sub S squared minus 2N over M squared times the sum from S equal 1 to M of F sub S. But of course, that's just the first frequency moment, so that's just equal to N plus N squared over M squared And so this entire thing is just equal to f sub 2 divided by m minus n squared over m squared. Okay, so if you could compute the second frequency moment, you could also compute the variance in the occurrence of elements. So the variance is in the frequency vector. And as one final one, because as mathematicians, we like to count 0, 1, 2, infinity. If you take the limit as p goes to infinity of fp of 1 over p, well, that's going to be equal to the limit as p goes to infinity of the sum s equal 1 to m, fs to p, 1 to the p. That's just the frequency of the most frequent elements. And it's elements because you might have two elements that have the same frequency. And in that case, they both be counted. Okay, so this is the general problem that we care about. So we care about getting the stream and we're counting how many times different items appear. And there are some frequency moments we care about. So start with the F0. And so we already know how to do F1. And we'll talk about F2 sketching a little bit later. Probably not today. If I'm being honest, it's not going to happen today. But we're going to talk about F2 sketching tomorrow. And we're going to talk about F0 sketching today. So we talked a little bit about this in our Whirlwind intros, and I spent a little bit too much time on sketching during my intro. But this is basically the distinct elements problem. And well, what are the different solutions? So we went over this last time, but we have an O of M space solution, which is just to keep a bit vector. And if an element appears, you set that bit to 1. If it doesn't appear, well, it stays at 0. We also have an O of N log M space solution. And this is your store list. Store a list of items seen. Or hash table or whatever. But you just store all items you've seen. Each item takes log M space because you need that many bits to specify which item it is. And you're storing n of them. Our goal here is to get something that's logarithmic in both of these. Space. And we may not actually achieve this, but that's sort of what we're aiming at. It's just like being logarithmic in both n and m ideal. But unfortunately, we can prove that this is not achievable. So there's a lower bound. So the claim is that any exact deterministic algorithm must use at least m bits of memory on some sequence of length m plus 1. Okay, so if you have a sequence of length m plus 1, you have to use at least m bits of memory, and so this goal is not achievable. Well, let's prove this. So what can we do? So assume, oh, wrong color. Let's start by assuming, for the sake of contradiction, that an algorithm uses less than m bits of memory on all such sequences. And well, let's recall that the power set has cardinality 2 to the m. So let's call this power set of this has cardinality 2 to the m. So these are just like all different subsets. And we know that the unique set of A1 through AM can be any subset except the empty set. Subset except the empty set, assuming that our stream is non-zero, of course. So we have 2 to the m minus 1 possibilities. Now, this is a little bit of a problem, right? Because we're only using less than m bits of memory, so we only have m minus 1 bits of possible memory states. But we only have 2 to the m minus 1. And note that this minus 1 is up in the exponent, not not outside of the exponent. Possible memory states. So less two by pigeonhole, two different subsets S1, S2, which are both in this power set, must have the same memory state. And this is just by pigeonhole. So that implies, of course, that the size of S1 is equal to the size of S2, because otherwise our algorithm would be wrong. But now we have two different sets that have the same memory state and have the same size. What happens if the next item in our stream is something that's in one of the sets but not in the other? And that provides a contradiction. So let B be in S1, but be not in S2. Well, land S1 union B. So after we add that to as the next item in the stream, it's just S1. So S1, this cardinality is, of course, just the cardinality of S1. And we know that S2 union B, well, that's going to be bigger. So we know S2 union B, oh, sorry, not B1, just B. S2 union B is going to have size S2 plus 1. But because the algorithm has the same memory state on S1 and S2, well, it has to have the same memory state when you add another item to the stream. And therefore, it must give a wrong answer on one of them. So, but the alg will have same memory state after adding B. So it must be wrong on one of them. Okay. So this is impossible. Now we're all sad, this is impossible. Should we just all pack up and go home? Well, no, because we can sometimes afford some small amount of error. And it turns out that if we let give ourselves a little bit of error, we can do significantly better. So I am going to consider, let's consider an idealized streaming algorithm. Consider an idealized streaming algorithm. Let's call this ISA since we'll use this later. And for the record, this is roughly speaking from Jelani Nelson's book on sketching. This is not in our textbook. Okay, so the first thing we're going to do is we're going to pick a random hash function h from m to the interval 0, 1. Now, obviously, this is an idealized hash function because we can't actually store a uniform random number between 0 and 1. And we're also not going to worry about any independence. We're going to assume that they're all completely independent. This is perfectly random, etc. So this is a magical hash function, but life is a little bit easier for doing our computations in this land. So what we're going to do is we're going to calculate z is going to be equal to the minimum over I in our stream of h sub I. Actually, I think I might have meant h of a sub I, something like that. And then we're going to output 1 over z minus 1. And we're going to show that this gives you an estimator. So let's call the script s unique of a1 through an, which is going to be equal to b1 through bd as a set. Okay, so there are only d distinct items in our sets, even though the stream might have linked n. And well, then what we know is that h of b1 through h of bd, well, that's just going to be x1 through xd, iid, uniform random variables on 0, 1. And we know how to work with those. There are all sorts of probability techniques you can use to work with those. And so if we now let z to be equal to the minimum over xi, such that I is equal to 0 from 1, and we're going to let z be this value. So let's prove a lemma first. Or actually, we're not going to prove this lemma. This is just a lemma from probability theory that I'm going to state because it's going to be useful. So if x is a non-negative random variable, then the expectation of x is going to be equal to the integral over this range of the probability that x is greater than x. dx. Okay, so this is a standard result in probability theory. I think there might be a proof in the book if that's, or I guess this isn't in the book, but it's in any standard probability text. So our claim now is that the expectation of z is going to be equal to 1 over t plus 1. And well, how do we prove this? By integration. So we know that the expectation of z is equal to the integral from 0 to infinity of the probability that z is greater than lambda d lambda, which is equal to the integral from 0 to 1 of the probability that for all I, xi is greater than lambda d lambda, which is equal to the integral from 0 to 1. Well, these are all independent, so we can just multiply together all these probabilities. Probably xi is greater than lambda d lambda, which is just equal to the integral from 0 to 1 of 1 minus lambda to the t d lambda. That's, of course, just by the PDF of, well, the uniform PDF. And so that's equal, after you do the integration, minus 1 minus lambda to the t plus 1 over t plus 1 from 0 to 1, which is equal to 1 over t plus 1. Okay, so this is just a simple result because if you take a bunch of uniform random numbers, in the expectation, the minimum is about 1 over t plus 1. So easy enough. But that's not all we want. So we want our estimate to have some guarantees on like how close we are. And so in order to do that, we need to work on its variance as well. So if we claim, our next claim is going to be that the expectation of z squared is equal to 2 over t plus 1 times t plus 2. And the proof is, oh, hello, is there a question? I think someone's unmuted. If you have no question? Okay. Oh, wait, why did I write t? Yes, I mean to use d everywhere. Sorry about that. Let me fix all that. D plus 1, d plus 1, d plus 1. Yeah, so thank you for catching that. Did I use t anywhere else? No. Okay. Yep. Okay, so 2 over d plus 1 plus d plus 2. So then the expectation of z squared is going to be equal to the integral from 0 to 1 of the probability that, well, z squared is greater than lambda d lambda, which is equal to the integral from 0 to 1 of the probability that z is greater than the square root of lambda d lambda, which is equal to the integral from 0 to 1 of 1 minus root lambda to the d lambda is equal to 2. So just doing lots of, so there's a lot of uninteresting calculus here, but let me write down all the important steps. So that's 0 to 1, ut u minus 1 du. So if you just do a u substitution where we let u be equal to 1 minus lambda, that's what we're doing there. And that's equal to 2 times integral from 0 to 1 u to the t, 1 minus u du. And this is going to be equal to 2 times, well, after all these are all d's. Sorry, I changed my notation midway through and it didn't actually fix it in my notes. So after all of this, if we do all these integrations, and I'm not going to bore you with, you end up with 2 over d plus 1 times d plus 2. Okay, so these are all particularly uninteresting proofs. Since they're all just applications of probability, we're going to figure out the moments, basically. But so now the important part is that then we know that the variance of z is equal to the expectation of z squared minus expectation of z squared is equal to t over t plus 1 squared d plus 1 squared d plus 2. I really apologize. I want to change all my notation, and then I changed half of it. And now I'm just going to be confusing myself this entire lecture today. D plus d over d plus 1 and d squared plus d plus 2 is less than 1 over d plus 1 squared. And now that we have this, what we can do is now we can do the averaging step. So previously that was just effectively using one hash function, and now we're going to average a bunch of these. So we have an averaging algorithm, and we're going to call that, well, let's call it AA. We'll use copies of list averaging algorithm later actually as well. And what we're going to do is now we're going to run a bunch of these. So we're going to run Q is equal to 1 over epsilon squared eta ISAs in parallel. Remember, ISA is what we call this idealized streaming algorithm. So we're going to run a bunch of these copies. And then what we're going to do is we're going to let Z bar is going to be equal to Q times the sum from I equal 1 to Q of Zi, where our Zi comes from the ISAs. And lastly, instead of outputting 1 over, we're going to output 1 over Z bar minus 1. So we're just taking the average, and this is going to then give us some guarantees on how close we are to our answer. So first, note that the expectation of Z bar is still equal to 1 over D plus 1. And we know that the variance of Z bar is equal to 1 over Q times D over D plus 1 squared, D plus 2 is less than 1 over Q times D plus 1 squared. So then by Chebyshev, we have that the probability that Z bar minus 1 over D plus 1, this distance, probability that's greater than epsilon over D plus 1 is less than D plus 1 squared over epsilon squared times 1 over Q times D plus 1 squared, which is equal to eta by definition, by our definition of Q. Okay, so we ran enough copies of lists that this probability is going to be small. And now our claim is that this probability, let's see, that 1 over Z bar minus 1 minus D, the probability of that is going to be greater than epsilon over T plus 1 is going to be less than D plus 1 squared over epsilon squared times 1 over Q times D plus 1 squared. It's going to be equal to eta still. Oh, sorry, not eta. Copied down the wrong thing. It's going to be less than, okay, let me fix all this. So this is going to be greater than some order of epsilon times D. That's going to be less than O of eta. Okay, so what are we doing here? So it's pretty easy to show, well, the expectation of our Z bar, which is an average of a bunch of independent runs, is of course going to have low variance and all that. But what we're actually trying to show is that our estimator 1 over Z bar minus 1 has similar sorts of guarantees, which doesn't always follow because, of course, when you take reciprocals of random variables, the variances don't always play nicely. And so we need to explicitly bound this. And so let's do that now. Okay, so let's prove this. Well, what are we going to start with? Well, we're going to start with the probability that Z bar minus 1 over D plus 1 is greater than epsilon over D plus 1, because that's something we know. So we know this is less than eta. Well, what is this equivalent to? Well, this is equivalent to saying that the probability of Z bar times D plus Z bar minus 1 is greater than epsilon. Okay, so those two are clearly equivalent. And we also know that the probability that 1 over Z bar minus T minus 1 minus D minus 1, D minus 1 is also greater than epsilon over D plus, over Z bar. So that's also less than eta. Those two are clearly equivalent. And lastly, we make use again of the fact that with probability 1 minus eta, Z bar is less than or equal to 1 plus epsilon over D plus 1. That comes directly from up here. And because that's true, we put these things together, and we know that the probability that 1 over z bar minus d minus 1 is greater than epsilon times d plus 1 over 1 plus epsilon is less than eta. And why is that? That's because if we had epsilon times d plus 1 times 1 over 1 plus epsilon, that's just 1 minus epsilon plus epsilon squared over 2 minus some o of epsilon cubed. So that's equal to epsilon plus d epsilon plus o of epsilon cubed, which is equal to o of epsilon times t. And so because that's true, we know that this thing here is o of epsilon times t, and this thing here is clearly o of eta. So from all this, we can conclude that with high probability, our estimator is within a factor 1 plus o of epsilon of 1 plus d. And what's the space complexity of this estimator? Space complexity is O of 1 over epsilon squared eta. Is that right? What have I missed here?
What's t again?
Oh, do I have a t again?
Yeah.
All right, where's my t?
We go epsilon times t.
That's a d again.
Yeah. It also with up.
Everywhere where I write t, you should think d.
Yeah.
Yep. But yeah, so this would almost be the space complexity, except that we didn't store any space for a random variable doing 0 and 1. Okay, so this is an idealized hash function in the sense that, well, if we could magically somehow store these completely uniform random hash values, well, then this function would work. But it doesn't work in real computers because we can't actually store numbers exactly. And so if we want to do something that's not idealized, we'll have to get rid of the assumption that it actually maps to a uniform random number doing 0 and 1. But well, this gives us a algorithm that gives us, with high probability, a good estimate of the a relatively good estimate of the number of distinct elements. But you'll notice that here the probability of failure is here in the denominator, and that's actually a pretty big amount, because that means that if we want a really high, not only do we pay for how much error we allow, but we also pay for this probability of failure. And ideally, we'd want to decrease that. And it turns out there are nice ways of doing that. And to do that, I'm going to introduce another method, which is going to be the bridges. So instead of just using eta to give instead of doing a bunch of the examples, so instead of doing 1 over epsilon squared eta, where eta is the actual failure probability that we care about, we're going to instead do this with some relatively large eta. So we're going to allow relatively large probability of failure and take a bunch of medians. Yep.
Is there a reason that we run them in parallel?
I mean, basically, you're doing this independently. So because we need these all to be independent random variables, we need each of the different ISAs to be independent in order to average them together. So that's what we mean by the term parallel here. So what else can we do? So a slightly more advanced method would be to instantiate S is equal to, say, 36 log of 2 over delta independent copies of the averaging algorithm. With eta is equal to 1/3. Why do we choose that? Because that means that we're allowing for a fairly high probability of error. But the sort of strategy that we're going to do instead is we're going to do a bunch of these, and then with high probability, the median is actually going to fall in there. And so that's a way that you can improve the failure probability from 1/3 to some smaller number while paying less of a price, right? In terms of the number of times you have to do it.
Yeah, that's what we want.
Delta is the error probability that you want. So this will become a little bit more clear when I make the claim. But yeah, so what we're going to do is the delta is some variable to be defined. Or what we're going to do is we're going to output the median, d hat, of all of these estimators for j equal 1 to s, where instead of our zj being the output of our ISA, it's now the output of our averaging algorithm. Is the jth output of the averaging algorithm, which we're now running a bunch of independent times. And now the important claim is we're now going to have the probability that d hat minus d is greater than epsilon d is going to be less than delta. So delta is our new failure probability instead of eta. And basically what we're doing is we're running this algorithm that has a relatively high failure probability, a failure probability of 1/3 many, many times. But if you think about it, if you run an algorithm with a failure probability of 1/3 100 times, well, that means on average, you're going to have 33 failures. But if you can show that these failures are evenly distributed, or in order for the median to be a failure, that means that it had to have failed at least 51 times. And that's very unlikely. And that's what we're going to quantify now. So this probability that it's less than delta. And so let's actually quantify that. So the proof here is going to start by, well, using indicator variables. So let's let yj be equal to the set from either 1 or 0. It's 1 if 1 over zj minus d is greater than epsilon d. So basically, it's 1 if it fails, and it's 0 otherwise. And we just need to count up the number of failures. So the median fails if at least half of the yj are equal to 1. That is to say, if the sum over j equal 1 to s of yj is greater than s over 2. But of course, this is unlikely because we know that the expected value of yj is just equal to 1/3, right? Since that was our failure probability that we set. So note that means that the probability that yj is greater than the sum of those is greater than s over 2 is equal to the probability that the sum over yj minus s over 3 is greater than s over 6. Okay, so the deviation from the expectation. But now, what do we do whenever we're trying to bound deviations from the expectation? Well, we have a bunch of bounds that we could use. In this particular case, we're going to use Chebyshev again. Oh, wait, are we going to use Chebyshev? No, we're going to use Chernoff this time. But basically, we use some tail bound, some large deviation probabilistic tail bound, and we can bound these failure probabilities. So we're going to use Chernoff here. And what we're going to do is, first, let's simplify by using the stronger assumption that the expectation of yj is actually equal to 1/3. So that is a higher failure rate. Just to make them, you can carefully work through it with the less than bound, but we're just making the error rate higher, and so it doesn't actually, so it only hurts us. So this is going to be equal to the probability that the sum over yj minus the expectation of the sum over yj is greater than 1/2 of the expectation of yj. Well, that's less than the some Chernoff bound. So this is a slightly different form of a Chernoff bound than the one in the textbook, but it is another one of the various forms of the Chernoff bound. Exponential of minus 0.5 squared times s over 3 divided by 3, which is less than delta by construction. Okay, so what have we done? So instead of just in the case up here, we had to take 1 over eta independent additional copies in order to get the error probability down. Sorry, not the error probability. The error probability, the chance of failure down. You had to take 1 over eta independent copies. Here, instead, we just set eta equal to 1/3, and now instead we don't actually need that many copies of it in order to using this median method in order to get the error probability down. So once we do that, the space complexity O of 1 over epsilon is going to be 1 over epsilon squared, log of 1 over delta, well, times, unfortunately, whatever the space complexity is of the 0, 1 thing, of the actual random variable, because we use an idealized hash function. But so instead of having a 1 over eta term in the denominator, now we have a log of 1 over delta term, so which is somewhat smaller. Does that make sense? That all?
How do you compute the median? You have to store all of the results.
Yes, so that's why this is taking up that much space, because we're storing all of these results. Because we have to do we have to store this many independent copies. Yeah. Yeah. And in the previous case, when we were taking the average, we of course also had to store all the results of that average. And here we're doing averages first, and then we're taking a median of a bunch of these averages. And that turns out to be more efficient than just taking the averages. So you can do it by just taking more averages, but it's actually more efficient here to take a median of averages. Which is something that you'll see sometimes in the design of these sorts of algorithms, and which may come up on your problem set. Like sometimes you want to take averages, and sometimes you want to take medians, and there are reasons you might want to do both. So for example, if what you're interested in is improving your failure probability, well, so long as you have some method that has failure probability less than 1/2, then in theory you can do this sort of median trick to decrease your failure probability by just taking the median, because you know if you do it a bunch of times, then with high probability more than half of them are correct. Whereas, of course, if you're trying to decrease the variance, well, in order to bound the error amount, well, oftentimes that you'll make use of averaging instead, because that allows you to decrease the variance of your estimator. Okay, let's see. How much time do I have? I have 13 minutes. Okay, so what I'm going to do now is, so that presentation was from Jelani Nelson's book. I'm going to also present the presentation from our textbook, because there's some things that are slightly different. And the next time we're going to see a completely non-idealized version. So in the next thing we're going to do, we're going to consider a non-idealized algorithm that isn't very good. And then on tomorrow, we're going to see a non-idealized algorithm, which is actually good. So consider the following algorithm. Consider the following algorithm from the book. And we're going to get rid of this idea of using an idealized hash function. We're going to use a real k-independent hash function of the kind that we've been constructing over the last couple of days. So consider the following algorithm. And this is in your book. From book. So the first thing we're going to do is we're going to have the same setup, be a string. I don't think I need to repeat the setup. It's all exactly the same setup. So same notation as before. For the stream. What we're going to do is we're going to pick a 2-independent hash function. So we're picking a random hash function from a 2-wise independent family. Let's call this H from little m to big M, where big M is bigger than little m. And then we're going to output Z is equal to big M divided by the minimum over I in our stream, H of AI. And let's just go ahead and call this thing the min to make life easier. And this is going to be an estimate for D, number of distinct items. And just as a note, let's call S to be equal to the set of all hashes, B1 through H of BD, is a set of D random and pairwise independent. Pairwise independent uniform values from our range. And the claim that we're going to make is actually somewhat weaker than the claims we've been doing with our idealized hash functions. So the claim is just going to be that with probability at least 2/3 minus D over M, we know that Z is greater than or equal to D over 6 and less than or equal to 6D. Okay, so this is a significantly worse algorithm than the ones we've been describing, where we can get epsilon close to our actual value. Here, all we're saying is that we're going to give an estimate that's within factor 6 of our value, which is much worse, but it does make the analysis a little bit simpler. And as I was saying, we're going to show how we can take these sorts of ideas and build on them to get an actual an algorithm with similar guarantees as to the one we just solved. But let's first see this easier algorithm, because it really shows some of the proof techniques that you have to make use of. So proof. Well, note that this is equivalent to showing that m over 60 is less than or equal to the min is less than or equal to 6m over d. Okay. Oh, and just for the record, you notice that we're dividing by m often, or we have this m up here. Well, that's just because, of course, if you're normalizing 0 to m minus 1 down to 0 to 1, that's what you do, roughly speaking. Okay, so what are we trying to do? So we have some set. We have m over d, and we have m over 60, and we have 6m over d. And notice that the minimum's here, min is here, if there exists some I such that h of bi is less than or equal to m over 60. And the minimum is here. The min is here if for all I, h of bi is greater than or equal to 6m divided by d. Okay, and we can do, actually, let me put that in a different color. Put that in a different color. So let's first do the left-hand side. So the probability that the min is less than or equal to m over 6d is equal to the probability that there exists some k. I don't know why I used k there instead of I, but I think I did. So let me just keep it that way. H of b sub k. Let me actually change it here, because otherwise I could easily confuse someone. B sub k is less than m over 6d, because it's a minimum, so you only need one of them to be smaller. And this is less than or equal to the sum over equal 1 to d of the probability that h of bi is less than or equal to m over 6d, which is of course less than or equal to d times the ceiling of m over 6d divided by m. And so this is by uniformity over m. And this is less than or equal to, and then using a union bound, less than or equal to 1 over d times 1 over 6d plus 1 over m, which is less than or equal to 1/6 plus d over m. Okay, so that one was pretty easy. And now all we need to do is bound the other side as well. So how do we bound the other side? Well, what we do is, well, use the same strategy. The probability as the minimum, the probability of the minimum being greater than or equal to 6m over d is equal to the probability that for all k, I think I used k here again, so let's change that to k. K. The probability that for all k, h of bk is greater than or equal to 6m over d, which is equal to the, so what we're going to do now is this analysis is a tiny bit harder. We're going to have to make use of indicator variables like we did in the previous slide. So what we're going to do is let me do all this aside in red. So let's let yi be the indicator variable, 0, 1, 0 if h of bi is greater than or equal to 6m over d, and 1 otherwise. And note that y is going to be equal to the sum over I equal from 1 to d of our yi's. And so when you do this, you'll note that this entire thing is just equal to the probability that y is equal to 0. Wait, did I get that backwards? 0 if it's greater than or equal to, so all of them would have to be greater. Yes, okay, no, that's correct. Okay, so we have all these probabilities, and then what we're going to do is we're going to bound this probability, of course. So this thing here is less than or equal to the probability that y minus the expectation of y is greater than or equal to the expectation of y. Okay, that's a sort of weird way of writing this. Basically, what we're saying is that, well, in order for it to be 0, it has to be at least the distance, its expectation away from its expectation in order for it to be 0, right? Yeah, so it's a sort of weird way of saying it, but when you rewrite it this way, well, clearly this gives us a hint as to which. Yeah. And so this gives us the ability to use Chebyshev again. So if we now we can use Chebyshev. So Chebyshev to get that this is less than or equal to the variance of y divided by the expectation of y squared. So what? Of course, now we need to compute these things. So note that the probability of yi is equal to 1 is equal to the probability that h of bi is less than 6m over d, which is greater than or equal to 6m over d divided by m, because those are like all the different possibilities. They're just taking that chance. That's equal to 6 over d, which implies that the expectation of yi is greater than or equal to 6 over d, and the expectation of y is greater than or equal to 6. And let me go ahead and write out that. Also note that, I guess I should have put all of this in red. This is all on the side. Also, we have that variance of y is equal to d times the variance of our yi's, and this is by 2 independents. So note that we'll show us a little bit more detail next time, but you actually do need 2 independents for this, because otherwise you can't multiply the expectations the way that we need to in order for the variances to just be.
The assumption.
Yes, yeah. So we're assuming 2 independents, and so this is what we're making use of now. And then we have that the variance of yi is equal to the expectation of yi squared minus the expectation of y squared of yi, all pretty standard stuff. So expectation of yi minus expectation of squared of yi. And note that, of course, that's because y is an indicator variable, so the expectation of it squared is just the expectation of it is less than or equal to the expectation of yi, and so therefore the variance of y is less than or equal to the expectation of y. And together, this allows us to go from here to that's less than or equal to 1 over expectation of y, which is less than or equal to 1 over 6. Now, clearly, we have a bound of failures on either side. One of them is bounded by 1 over 6 plus d over m. The other side, the failure is bounded by 1 over 6. So plus with probability at least 2/3 minus d over m. D over 6 is less than or equal to z is less than or equal to 6d. Okay, so what do we have now? So this means we have a constant factor approximation that succeeds with probability greater than 1/2. So it's pretty easy to use some sort of median trick to, of course, increase the failure probability or decrease the failure probability down arbitrarily now, right? You could just take a median of a bunch of these. But getting the error down from a relative error of 6, that's a lot harder. And so that'll be something we'll do at the beginning of the next class. We'll do a slightly different version of this. So we'll do the same analysis, but with a slightly different estimator, and then show that we can then expand that estimator out to one where we can get it down to a 1 plus epsilon approximation instead of this constant order multiplicative approximation. Yeah, so that will be next. Shouldn't it be variance of yi squared in Chebyshev? Is that variance of y squared? I honestly don't remember, but class is over right now. Let me double check that afterwards. So thank you all very much. I will see you tomorrow. Yep.